conceptual question for chapter 11?
Because you said that the next step would be kind of like conceptual question.
Well, an example would be look at valence bond. How is a bond described in valence bond theory? Or how is a bond described in molecular orbital theory? And so that would be a conceptual question. Or, what is stronger? A sigma bond between two atoms or a pi bond between the same two atoms? Those would be conceptual. Plus, we're going to be doing some more conceptual type stuff today. Okay, other questions?
Are we going to still stay on chapter 11 too?
We're moving on already, yeah. We're moving on to chapter 16 now. But chapter 16 requires chapter 11 stuff. So it's application. And so we've been talking about bonding theories. The next thing we're going to do is we're going to apply it to something. All right. When we're thinking about like properties, let's talk about that for a second. You remember this from the first week of class? Properties. Chemists are trying to correlate properties of what? Chemists are always trying to correlate properties with Nobody remembers? In a way, yeah. I mean, the properties are obtained from experiments usually, but also you want to be able to predict properties too. And so we need to understand how properties are related to what in order to make predictions. Well, what do properties depend on? Composition, yeah. Composition. But, for example, diamond and graphite have the same composition as carbon. The properties are quite a bit different because of what? The structure. Right. That's good. Remember. Structure. And so we want to be able to correlate properties with structure, based on the composition. And so we've been talking a lot about the structure and trying to draw out structures and this kind of stuff. So what we want to do is we want to, initially chemistry is like a two-pronged type of deal. We see what the properties are, and then we see what the composition and structure are, and then we make an association, right? The two-pronged approach is you use, factual knowledge, right? It's kind of memorization, in addition to theoretical knowledge. You can't do everything theoretically. For example, HI. Prove to me what state HI is. If I'm looking at pure hydrogen iodide, is it solid, liquid, or gas at room temperature? Do you want to use theory to do that, or do you just want to Google it and then see what state it is? Well, you probably want to use theory, right? But do you think that's an easy thing to answer theoretically? Probably not. And so this is why we have this two-pronged approach in chemistry. And so the first part of that is to look, the properties are facts. If you did some measurements of properties, those are facts. And whatever theory we have, those theories have to agree with facts. Right? And so this is what we're doing today. Today's class is going to be a little different. Rather than me sitting up here and talking about chapter 16, I'm going to ask you to do some work here. And we're going to compare two acids, HCl and HI. Hydrochloric acid and hydroiodic acid. Which one is stronger? Is HI stronger acid or HCl stronger acid? Normally I'd just say HCl. HCl is going to be a stronger acid than HI. Automatically I'd say that because of what I think about the structures of those two. But does that agree with fact? The fact is, which one's a stronger acid, HI or HCl? HI. And so there are certain, structural characteristics that I was thinking about that made me think HCl is stronger, but in fact HI is stronger. And so what we're going to do is this. You're going to analyze these, series 1. So the first thing we're going to do is we're going to draw out the Lewis structures. Right? And then we're going to look at, and polarity. Remember polarity? Bond, polarity, molecular. Well, there's only one bond in this. The molecular dipole and the bond dipole are the same thing. So we look at Lewis structures and polarity. And then what else do we get? We can get the formal charge and oxidation state. And so by looking at that, and then, that's all we need in order to predict some chemical properties. But before we get to chemical properties, let's take a look at some physical properties. Physical properties, what types of physical properties would you be interested in? You'd be interested, is it a solid, liquid, or gas, right? Solid, liquid, or gas. Whether it's a solid, liquid, or gas is going to be largely dictated by its melting point and boiling point. It's going to be hard to predict. If somebody asks you, hey, what's the melting point of HI? You going to use some theory to figure it out, or are you going to use an experiment to determine it? You're going to use experiments, so this is just like memorizing facts, right? And then once you figure out what the melting point is, then you try to correlate it with something structurally or something compositionally to make an association, so that if we see some kind of association similar to that, we can make a prediction. Like, for example, HI might have this melting point, but HCl would have a higher one or a lower one, based on structural or compositional analysis. Okay. And so we make use, once we have some reference facts, a lot of people think, oh, memorizing facts is a waste. No, memorizing facts is very important because you have those as reference points. Like if you're driving, and you memorize, oh, there's a mountain over there, when I first moved here, I was very confused. Am I driving north, west, south? You can follow the sun or something like that. I had no idea because where I grew up, there's a big mountain there, and that big mountain is north. And so if you go towards that mountain, it's north, right? And so it's very easy for somebody to get the bearing because they can see, right? And so that's the same thing. If you have some facts memorized, then you have some kind of bearing, and then you can make judgments about other things. And so this factual knowledge is very important. Memorizing some facts is very important. But we don't have to here, melting point, boiling point, I don't know. HCl, pure HCl, is that a solid, liquid, or gas? It's a gas, right? Hydrogen chloride gas. How did you know? Well, you memorized it. All right, if you didn't have that memorized, then predicting something for HI would be very difficult, because if you know HCl is a gas, then probably HI is it could be a liquid. That's possible. It might be a liquid. Because what dictates melting point or boiling point? What dictates these are intermolecular forces. Intermolecular forces we haven't gotten to yet, but you should already know, the three major ones. What are the three major intermolecular forces that you should already have learned in Chem 4? There's one. As far as IMFs are intermolecular forces. go, there's London or dispersion forces. Sometimes people call them London dispersion forces. About London dispersion forces, the way they work is there's something called an instantaneous dipole. And what that instantaneous dipole does is it induces a dipole in an adjacent molecule. And so we have instantaneous dipole, induced dipole attraction, call it. And what this depends on is the number of electrons. You know, the more electrons there are, what happens is, you know, the bigger the electron cloud is. The bigger the electron cloud is, the more deformable it is. You know, the more deformable it is, we call it the more polarizable it is. Because when you create deformations in the electron clouds, you create, you know, charged regions, and those create or make it polar. That is, typically when we think of poles, we think of dipoles. You know, North Pole, South Pole. That would be a magnetic dipole. But we also have electric dipoles. Electric dipoles are positive and negative polar regions. We don't just have dipoles. We could have quadrupoles. Have you ever heard of a quadrupole? Quadrupole has like 2 north poles and 2 south poles. And we have monopoles. You know what a monopole is? Just has one charge, you know. So there's no positive region. Maybe it's all negative. It's like an ion. But anyway, the larger the number of electrons, as the number of electrons increases, then the strength of the London force increases. So here, it's because of this, you know, creating larger, what we call instantaneous dipoles by polarizing the electron cloud. And so we look, you know, things with stronger London forces are going to have higher melting points and higher boiling points. Things with weaker London forces will have lower melting points and boiling points. But we just don't have London. We have dipole attractions, right? Dipole. And so the bigger the dipoles we represent in different ways. We can use these delta pluses and delta minuses. These are partial charges, so not full charges. And so the bigger the dipole, the stronger the attractions. The stronger the attractions, the higher the melting point, the higher the boiling point. This is like when we were talking about bonds. You know, the more bonds there are holding something together, the more energy that it's going to take to break those bonds. Therefore, you're going to need a higher temperature in order to break those. So we got dipole. What else do we have? Hydrogen bonds. Hydrogen bonds are what? Hydrogen bonds are unusually large dipole attractions. This is this IMF stuff is in chapter 12, you know, the beginning of chapter 12. Talk about it now. Unusually large dipole attractions, just give you a brief overview now, and then we'll look at it a little bit deeper later. But it only occurs when we have hydrogen bonded to a fluorine. When hydrogen is bonded to fluorine, it creates an unusually big delta plus. This is still, it's not quite an ion. An ion would be a full positive charge. This is still a polar bond. But hydrogen, you know, the unusual thing about hydrogen is if fluorine pulls the electron density away from hydrogen, there's no inner electrons, there's no core electrons in hydrogen. And so as the electron's being pulled away, then something out here is going to see the nucleus straight without any shielding. So if it sees the straight nucleus, it's like a full positive charge. And that's, the full positive charge is going to be stronger interaction than a partial positive charge. Like this. The bigger the charge, the stronger the interaction. So we have HF, we have H2O, and we have HN. These have unusually big delta pluses on the hydrogens, unusually big delta pluses, depending on the angle you're looking at. Then we got the delta minuses over here, but it's primarily the hydrogens that are doing it. one that you probably didn't do too much about is ion dipole attractions. Ion dipole attractions, you know, a dipole is a partial charge, an ion is a full charge. So full charge, obviously. Ion dipole can be much stronger than this or weaker. Then H bonds. Typically people think of H bonds as the strongest, but no, they aren't necessarily the strongest. There could be stronger interactions, like ion dipole, or potentially weaker. And so there's a big range of these depending on how big the ion is, what its charge is, etc. We have one more called a dipole, ion-ion attraction. Ion and ion attraction you'd think is an ionic bond, but this was just a, IMF, not a real bond in that sense. And so you make some predictions, Some stuff you just look out, you just take a guess, HCl's a gas. I'm going to guess that HI is going to be a gas also, or maybe you'll guess HI is a liquid, or maybe a solid, depending on what you think about the IMFs, right? That's the best we can do. You can always look it up, though. If you look it up, then, whatever we come up with has to agree with experimental fact, that is, whatever we come up with in terms of composition structural analysis has to agree. Then we look at chemical properties. Physical properties, solid, liquid, gas, solubility, etc., electrolyte properties, whatever. Chemical properties, what types of chemical properties do we look for? Well, these are two acids, so acid-base properties for sure. But are acid-base properties the only chemical properties that we encounter, or are there more? We have acid-base, we have, what else? Redox, and we have metathesis. And so we lay out some of the properties, or some of the properties that we think we should find for HCl and HI. And one of the properties is both are strong acids, right? But HI is a stronger acid. And so what we want to do is we want to try to correlate something about the structure of these, or the composition of these, such that it's consistent. It makes sense that HI is the stronger acid. And so what we're going to do here is we're going to just try an application of what we've done so far in terms of analysis, and that is we're going to use valence bond. We're just going to do a valence bond analysis of both of these, and then just try to do it as detailed as possible to come up with some kind of reason why HI should be stronger, and both are strong acids. Okay? Something like that. Some of the other properties, like the metathesis and redox properties, they're going to be comparable in some ways. We'll look at those. And so, in other words, this is one application. One of the applications is just making a basic correlation between the structure and the properties. Okay, you're going to do this for HCl and HI. And then we're going to look at H2SO3 and H2SO4. And then repeat the analysis. And then for 3, we're going to look at HF. The question is, why is HF a weak acid? HI, HBr, HCl, those three are strong acids, very strong acids. But HF, where is that? It's weak. All right. And so, why don't you guys work together if you want, or work alone, and then see what you can come up with, rather than me telling you what's going on. See if you can figure it out, or start thinking about it at least, and then I'll do a progress check, and we'll come back to this and talk about it in detail later.